you with the stuff that we think you're supposed to know and see. So or more important than us knowing whether or not you know stuff, it's to help you guys figure that out, and then you can change your study habits and ask more questions or go to hours or not, depending on where you think you are in that spectrum. Because really, at the end of the day, it's all about you. What do you take away from this course? The third reason is that she said this and this was really obvious, but like studying actually helps you learn. So the act of giving you a midterm makes you study. A high stakes exam gives you this incentive, and this is actually a lot of how I work too. I'll give myself paper deadlines and stuff to actually make myself go off and do work. So we want the studying process is also like going over the material all at once on your own, helps you learn it. And we're going to talk about the best way to study for the midterm. In particular, I think the best way to study for this midterm is by doing problems. So we've given you a lot of problems already, especially on the homeworks, and we released a practice midterm yesterday that's easier in some ways and harder in other ways in the real midterm, but like it was our first draft of what the test is going to look like. So as you're preparing for this test, I recommend that you look at the book and you look over the lectures, but the primary thing, the thing that I think you'll get the most bang for your buck in terms of the time that you invest in studying is by going back over the homework problems, and especially the practice test that we released, on your own and just seeing if you can do those problems. And then if you can't, then go to the materials, the book, TAs, us, me, the grad TAs, and talk to us and try to figure out what's going on so that you can get to the point where you can do those. Because that's what the test is going to be like. Okay, so that's that last thing. So the best way to study is to do these practice questions. So I hope that answers the question from last time better. All right. So the next thing I was going to do is kind of go over the stuff from the beginning of the course, which are sort of the goals for the course that I put up in the first lecture. So this was what we hope you're going to get out of this course. And we're halfway through, so I hope that you're getting some of this stuff. And if you're not, we should talk about it. So I hope that you're starting to understand theoretical and practical approaches for building intelligent systems. We've talked about a lot of searching, and we started to get into the scoring in these probabilistic models, searching and scoring algorithms for producing intelligent behavior. And we've also talked so far about a couple of real-world examples. We've done closer studies and also kind of hand-wavy studies, sort of hand-wavy descriptions of different artificial intelligence techniques and how they're used to solve real-world problems. So for me, it's really important that you guys see how this stuff relates to problems you're going to face out in the wild, and that we talk about that mapping, because I think that's really important for actually using these skills 10 years later. So I don't want this to be a course where you just forget about it. I want 10 years from now, I want you to think, yeah, AI. Okay. So in that mind, like this is sort of the act rationally algorithm from before. Like you have the searching and the scoring. I'm trying to give you this high-level framework for how we can think about intelligent behavior, and then come up with multiple different specific instantiations of this framework, which sort of boils down to tricks and how we get all the actions, the order that we explore the nodes in the action space, tricks for how we represent that scoring function, and how we can learn it or how we can encode it in the system, and sort of where it all comes from. So I'm going to stop here. I have slides for the different topics on the midterm, and we can go through that. But I guess what I wanted to do, first of all, is go back, like given this sort of mission statement for the course and stuff, and here we are halfway through. What do you guys think of the course so far? What could we be doing better? And what did you like and what did you didn't like? What don't you like? Yeah?
The readings have some stuff that we don't go over in the homeworks.
Okay.
And the part to see how which the specific parts of the reading we should focus on.
Okay, so like a better focus.
So make the reading assignments more.
Okay.
Sections,
okay. Is it okay if I take notes? What's that? Do you mind? Okay, because that's actually pretty easy to fix for the rest of the semester. We can go through. Yeah?
Also, there's plenty of seats back here. Up to you.
You know what? I'll take notes on the whiteboard. Here. Sorry.
Sorry.
All right. Alignment between readings, homework, lectures. Yeah. So my bias has been to give you guys like chapters, like bigger chunks, and then we focus on subsets of that, but there's like usually more background in the textbook. What I can try to do is, I still like to do that because I think it's useful to because if people want to go deeper or read more stuff, to sort of know where to look. But what I can try to do is give more detailed pointers on the schedule to exactly what's really important for what we're actually going to focus on, of course. Thank you. Yeah.
I really liked having warm-ups, especially like if it was sort of ambiguous
Uh-huh.
questions. It was nice to do warm-ups.
Okay. Like the warm-ups. Thank you. Yeah, so that was people complained about that last semester, that we didn't have those warm-ups, and so we were trying to adapt in response to that. So I'm glad to hear it's working. Yeah.
As a first-time user of edX, I like the immediate feedback of the homeworks.
Uh-huh.
So
Knowing, yeah.
Go.
I like that too. And I think that's, again, talking about this metacognitive stuff, like it's important to let you guys quickly know whether or not you're getting it, and then you can figure out so theoretically this translates into better learning. I don't know if it does or not. Yeah.
Go along with that, it's really good not only do you get immediate feedback, but
Yeah.
you get immediate feedback and a chance to retry it. So
Yeah.
you kind of like have the chance to learn it again.
Yeah.
See if you're right.
Yeah.
And that way you don't do a whole homework wrong because you were wrong about that initial fact
Right.
and had no idea of knowing.
Right.
It was great and easier too for everyone.
Okay. So that was kind of because the thing the trade-off that we've been doing with this is that we've been not asking largely the types of questions that we can't auto-grade. So we had that one exception with the discussion forum post where we had you guys talking to each other, but like we've been not asking short answer questions and things like that, or derivations or proofs, which I think are good stuff, just because it's hard to have that be auto-graded, and we think the trade-off between that and getting the immediate feedback is sort of worth it. But is that okay, or do you guys wish there were more questions like that?
For a midterm, it feels weird not having questions like that, I guess.
I see.
Just because the immediate
Yeah.
feedback of a midterm.
So actually, I do have a few on the midterm where we're going to manually grade. So you'll type them into edX, but we won't get the answer right away. Yeah. Yeah.
I think this is like more for the last homework specifically.
Yeah.
For stuff where there's like more complicated mathematical calculations.
Yeah.
It was pretty frustrating not having a chance to like learn through that warm up, and I felt like I didn't really know what was going on when we were just had to like immediately go through.
So the warm-ups were too easy?
Yeah, I felt
Yeah.
like the warm ups
Okay.
expectations.
Yeah.
were very different.
Warm-ups and homeworks. So warm-ups were too easy. Easy.
Like too like high level.
Too
As,
high level.
conditional.
Okay, so we should try to make them more similar to each other. Yeah, we could do that. Yeah.
So on the projects,
Yeah.
is there such thing as 0.5 off or is it a whole point off?
It depends on the project. So we got some complaints about that in the first project. I sort of feel like that I don't know, like the rubric is in some sense, especially for like passing the test cases and stuff, we try to be pretty clear about what each question is worth. But we got more cognizant of that when we're grading the second project and the future ones. Yep.
Psychologically, it's the same thing with the project.
Yeah.
Psychologically, it's pretty easy to take a point off no matter how many points there are
Yeah.
for graders.
You just think that? Okay.
So if you make it out of 100,
Yeah.
it's not going to be as
Okay.
easy out of 20 or 10.
Okay. So you guys, okay, we'll talk about that with the core staff. Make projects out of 100. Out of 100. All right. Yeah?
Every so often there are things on the homeworks that just are not covered in class.
Uh-huh.
Markov blankets on this last homework.
Uh-huh.
Or in the reading stuff.
Things in homework. Yeah, but that's a good point, because I wish I had gotten that in lecture. Like, I think that's really important to know, and I didn't get to it. So making sure that things in the homework, it's going back to almost this first question, and the lecture, making sure the lecture covers what's in the homework, at least at some level. The lecture covers the homework. Okay, thank you. What else? Anything else, or should we get into our review? Yeah?
I think just going back to the idea of the warm-up.
Yeah.
I think the warm-up we had for this last homework was really good.
Uh-huh.
But we didn't have any sort of like numerical stuff in the warm-ups, so like how we had that and maybe like a small extra section on some numbers,
Mhm.
then it would have been like more prepared. But
Mhm.
like I think it was good.
Mhm.
The warm-up we did have was really good. It just
Okay.
didn't cover everything. guess.
I see. So it was good as far as it went, but we just needed to have
Yes,
some more
like
more
a slightly
questions.
more thing with
Yeah.
some numbers.
So you guys are asking for more questions. I like that. That's good. Okay.
Yeah, I
Yeah.
didn't think that it was too easy. I just
Yeah.
thought it would have been nice to have more like mathematical questions so that
Too
you
short.
could understand how to do those calculations without the pressure of having to
Right.
have a two-tracker.
Okay. Cool. I'm glad you guys, like, that's actually really, makes me happy that, like, not only are you say you're liking the warm-ups, but, like, the feedback of how to make them better. It sounds like you really want that, like that you're engaging with them and thinking about what we can do to make them even more useful. So I appreciate you sharing that with me. I'll leave you guys. You two pick it. All right, anybody else? Or should we go into review mode? Yeah? All right. So what I thought I would do for the review is I put up sort of the summary for each of the sections that we covered in class and which we're going to cover on the midterm. And then I thought you guys could sort of ask questions if there's things you want to go into in more detail. And then if we get through all that, we can go back and start looking at the old homeworks and maybe try to do them together in class. Because I think that, like I said, the best way to study is to look at the practice midterm and to look at the homework problems and the warm-up problems and just try to do them again. And make sure that you feel comfortable doing that. If you feel like you can do all the homework problems and the practice midterm problems, I think it's pretty likely you'll do well in the midterm. Okay, so there we go. So we sort of started with uninformed search. We had this abstraction of the state action space. We talked about breadth-first search and depth-first search. We talked about how to implement them. So there was that whole stack versus the queue. We actually implemented it in class, and the code for that is online if you're interested in it. We talked a little bit about complexity trade-offs. The book goes into that in more detail, but not too much stuff. I copied this from my own site. And then the next class was informed search. I'll take that out. So is there any questions about that stuff? Anything you'd like me to do in more detail? Do you want to look at
Like the complexity trade-offs?
Yeah, so like how much memory did it use and how much time did it use? So we could talk about it in terms of the size of the input space. So like how many actions are there in your state action space? But usually people talk about it instead in terms of search depth and branching factor. So at each state, how many other actions can you take to get to a new state? And how deep is your space in order to get to a solution? So B and D. And then we talked. I'm actually not going to ask too many questions about this on the midterm, but but the book talks about how to do this analysis for these different algorithms. The difference between that, between breadth-first search and depth-first search and A star, measured in those numbers. Yeah. Good. Okay. All right, and then we had informed search. So adding the high-level idea of informed search is that adding information helps us do better. Sometimes it helps us do much better. And we talked about sort of this trade-off between speed and accuracy. So with greedy search versus our A star search. So we sort of had greedy, and then we had Dijkstra's algorithm that made breadth-first search find the optimal path in terms of hops, or in terms of path cost. But it would still expand the whole search graph. And then we augmented that with a heuristic, so A star, which was expanding the lowest path cost plus heuristic cost to the goal. And what makes a good heuristic, being admissible and being consistent. Yeah.
Can you go over again, like what G and H are and what like
Mhm.
consistent is?
Sure. So I think I even have those slides open. Here. So an admissible heuristic never overestimates the cost to reach the goal. Why is that important? Yeah.
Because when you reach the goal, you will stop searching. You have to go back and see other things there.
Yeah. Right. So if you are overestimating the cost and then you actually go down that path, you find it was less than you really thought, if you actually find a path, remember one of our examples, we found a path that reached the goal, but it wasn't the optimal path. And if our heuristic lied to us and said, oh, this other path is overestimating the cost, it would never go back and expand it. It would stop because it would trust the heuristic. If it either underestimates or gives you the actual path, then if we found one path that actually reaches the goal, then we'll always, and there's a better one, we'll always know to go back and expand that other path and find it. So it guarantees that we're going to find the optimal path to the goal. All right. So then consistent was writing this out in formal notation where, so this is basically the triangle inequality. So this was the cost. The heuristic of the node has to be less than or equal to the cost of the node plus the heuristic at the following node. So consistency was a stricter requirement than admissibility. So it means, but it's actually pretty hard to come up with something that's admissible and not consistent. We had to, remember, I think I actually have the example up here. We had an example here where it was, remember the 8-tile problem, you're moving these blocks around, and you're trying to get them to be all in different orders. And then different heuristics for the total number of misplaced tiles, just how many are misplaced, versus the Manhattan distance, versus the Manhattan distance of 1, 2, and 3. And these are all admissible and consistent, but some of them are better than others, right? Because some of them give you more information about what's a good trajectory. There are tighter bounds on the true cost of the goal. They underestimate it less. And then we come up with this one that's admissible but not consistent, where it's a non-deterministic. So it was sort of flipping a coin between the two. The main thing I want you guys to take away from heuristics is not so much the difference between admissible and consistent, but like that you have to have consistency, and if you don't, then you're sacrificing optimality. So when you're coming up with heuristics, how do you know that, or how do you prove to yourself, like you guys were doing on the Pac-Man problem project, how do you prove to yourself that it's not going to sacrifice optimality? Or if it is, maybe it is, and maybe that's okay with you. Maybe it's such a good heuristic that even if it sometimes overestimates, like sometimes not being optimal is okay. So what I want you to do is be comfortable with making those trade-offs and knowing that you're making those trade-offs in practice. Does that help? Okay, yeah.
So can you describe, like at a high level, how, because you keep saying that consistency is a stricter condition than
Mhm.
admissibility.
Mhm.
So can you describe how something can be consistent but not admissible?
Yeah, here's our example of one that will never overestimate the cost to the goal, because
I mean consistent
yeah.
but not admissible, not admissible but not consistent.
Admissible but not consistent.
No, I'm asking about
yeah.
consistent but not admissible.
There's no such thing.
Well, the
So
practice midterm there was.
was there?
No, yeah, you could take like a regular admissible and consistent heuristic and then just add a really high fixed value to it, so it necessarily overestimates.
Uh-huh.
But each time you increase the step size, it's still increasing. Right.
Still remember misplaced tiles plus 10 million.
Yeah. Okay. Yeah. And then you're always overestimating,
Yeah.
but you're overestimating in a consistent
Yeah.
way. I see. So if consistent, and you're saying that would be a consistent heuristic,
Yeah.
but not admissible.
That makes sense, actually, yeah.
Okay. So it depends how we. Okay. So I think we're using. So if we use, let me get to the slide.
Actually, wouldn't that overestimate the final pass cost?
Yeah.
When you got to the final cost, it would all snap. You wouldn't have a heuristic term in your cost estimate. So you'd be like, oh, I thought I was going to pay 10 million to do this path, and actually I only have to pay.
Like technically 10 million to go from
Yeah.
the same point to the same point.
What do you mean?
Like your end location, if your constant term is 10 million,
Yeah.
then you're effectively overestimating a final step to get from your destination to your destination by 10 million. That wouldn't be consistent.
Isn't it equal then? 10 million is equal to 10 million? Because the cost to go from the same state to the same state is 0? Yeah.
Well, I think what it would make you do is overrank, like you'd basically ignore your path cost and only use the heuristic cost. So I think what that would correspond to would be greedy search in practice, I think.
Because like your changing heuristic would be non-zero for
Because-
zero step.
What's that?
just going back to like
Yeah.
these constant terms being inconsistent.
Yeah.
Because like for the final step, your changing heuristic would be non-zero for a size zero step.
Your final heuristic would be 0. Well, so I guess I was just thinking about, like, we should draw an example. Like, so you have 2 paths to the goal, and let's see, this is your start, and this is your goal. And you're trying to figure out the shortest path to the goal. And you expand this node, and you expand this node, and your heuristic cost to the goal is, let's say, maybe we should stick some more stuff in here to make it better. So like we had this kind of crazy example where you went like way out here, and then we came in here, right? And so this kind of looked good because you were going closer, but then really it was farther because you had to go out do this detour to get to the goal. And if you so we were thinking about what actually happens if you add a high constant cost to your heuristic estimate. So that means you would always be overestimating your path to the goal, but you'd be overestimating it in a way that would be the same for every single node in the graph. So if you expanded this node and you got, like, let's say this is 1 and this is 2, then my cost is 1 plus 10 million plus dist. Like I have my real heuristic in there too, right? From here to here. So let's say this is 1 plus 1. And I go over here, and this would be 2 plus 10 million plus 1.5. Let's say a dist from here to here is 1.5 plus 1.5. So,
Wait, isn't it?
yeah.
Lower it.
What's that?
The goal, the bottom one.
Oh, right. Sorry. 1.5. Yeah. So this, again, we'll make this 1, 1. So what we wanted to do then is to go over here and expand this node and realize that it's really far, like its heuristic cost from the goal is really far away. And then go over here and accept this one because it's less than the heuristic cost. So so if we have this 10 million in there and we're comparing it all the time, would it just cancel out?
Well,
Yeah?
even if you ignore the idea, the notion of going from your goal state to your goal state
Yeah.
as like a non-consistent step,
Yeah.
part of the definition of a consistent heuristic is that your heuristic for the goal state is 0.
Yeah.
Right, because,
By
yeah.
definition,
So then you could-
we tend to-
Yeah, so maybe I should say something, right. So if we just look at the definition of this, the heuristic you defined is not consistent because
Yeah.
it by this formal definition of the word consistent. However, I think and I think we can all agree on that, right? Like it just doesn't work. But the question I was thinking about, and I don't actually know the answer, is even if it's not consistent by this mathematical definition of consistent, would it still lead the optimal path, even though it overestimates the cost of the goal? Yeah.
You could easily make that one consistent by just saying it's 10 million plus number of misplaced tiles, or 0 if it's the goal state.
Yeah. No, but even then, it's not because it's overestimating. It just can't overestimate. So if we're, but the question I was trying to figure out is like if we overestimate, but we do it in this kind of funny way, in this consistent way, even though it's not the technical term
I
of
think it would still find the
consistent,
right
would it still find the right path? And I think it would. I think what I'd like to do actually is take this offline and code it up and see.
Well, 'cause
Yeah.
if you don't define your goal state as being when
Yeah.
your heuristic returns 0, you define your goal state as I'm at the goal state.
Yeah.
Then it doesn't matter like whether or not that term you make that
Mhm.
term technically 0 because every other term will, you're like you said, be consistently off.
Right.
Yeah.
So it'll just cancel out when it's doing the
I
comparison.
think so.
Yeah, I think you're right, but I think I would like to code it up and see. When I'm not sure about something, I always go back to the code. And I don't think I want to use the class time to do that, if that's okay with you guys. So I'll upload it, and we can try it out and see what happens. All right. Yeah.
So does this mean that you cannot have a consistent heuristic that
Is not
is
admissible.
not admissible?
Yeah.
So that there's a mistake on the practice test.
Okay.
It's a
We should check it out. Okay. Fix mistake on practice text. Mistake on practice test. Yeah, and there may be more mistakes. We did test the practice test. We had a couple of TAs take it, but we're putting more of our testing effort into the real midterm than we did in the practice test. So, and I think the process of finding mistakes is also a good way to study, so I hope that doesn't break things. Yeah?
So just conceptually what it means to be consistent,
Mhm.
does it mean that if you transition from one state to another, your heuristic doesn't get higher? Is that what it means, or?
Well, it could get higher as long as it doesn't underestimate the overestimate. I always get it backwards. The true cost. So it could give you one value, and then when you go over here, it could give you another value. But as long as that bound is never high, so this value in this example would be a lower heuristic estimate to the goal from here to here than here, which is farther along the path. The heuristic would be higher, but in both cases, it should be, it should not overestimate. Both of those numbers would be bounded by the true cost. Does that make sense?
So, I don't know, I'm just having trouble, like, understanding, like, conceptually
Yeah.
what consistent means, like, as opposed to mathematics.
Yeah. So if you think about this example, so here is the true cost to the goal in the graph. Like, so let's say this is 1, this is 2, and this is 3. 1 plus 2 plus 3 is 6. Yeah. Okay. So for this node, if you're at this node, and let's not ignore going backwards and stuff, the true cost of the goal is 2 plus 3. Let's make it 5, because we're just talking about this node here. All right? Or maybe it's 1 plus 2 plus 3 if you go from the start node. Okay? But the heuristic is always the future, right? So it's 5. So my heuristic value here is 1. So my H1. Let's say this is node 1, and this is node 2. 1 and 2. My H2, let's say, is just like it's 3. So here, H2. So this is, here, I'll label it a different way. So this is 1, 3, 5. True cost, H2 and H1. So in this case, when I was at H1, my heuristic value is 1. When I'm at H2, my heuristic value is 3. So it went up from H1 to H2. But in all cases, it was under the value of 5. So it never overestimated the cost of the goal. And the reason that is important is because I will, it will not block off this path so let's say that let's say this was the optimal path to the goal. So let's make this, let's say 15. Let's say it's not matching Euclidean distance. We might not expand this node unless and then let's say it did overestimate. So let's say that my heuristic value here wasn't 1. Let's say that it was 150. Like I overestimated the cost to the goal. Even though the true path cost here would be 6, my heuristic would stop me from expanding this node anymore. And I would settle for this path here of 2 plus 15, 17 as the path that I return. So I would not find the optimal path.
I mean, I think my question is
Yeah.
just what is consistent mean? Like in words, like rather than like math or graphs or whatever.
Okay. What it means is I never overestimate the path to the goal. The consequence of that is that I can construct, like if I do, I guess what I'm trying to do is like a proof by contradiction or something. In other words, why would I not want to overestimate the path to the goal? If I did overestimate it, bad things happen, and there's an example of a bad thing happening.
Isn't that just admissible though, not overestimating path to the goal? That's like admissibility rather than consistency. I don't know, I can look it up after.
So explaining it intuitively, like I'm conflating the two. So explaining it mathematically, we sort of talked about how the important idea is that overestimating the path to the goal leads to behavior where the algorithm won't find the optimal path. And the simplest way to define that mathematically, or the sort of standard way, is this consistency thing. We can construct pathological examples like that probabilistic one where it's admissible but not consistent, but that stuff doesn't usually come up. So the important thing to hang your hat on is consistency, and it's almost not so terrible to be clear about the difference between admissible versus consistent as it is to say consistent versus not versus nothing. And because that's really where the bad thing, where the dragons are, when you don't have a consistent heuristic. Yeah.
The way I thought of it, I don't
Yeah.
know if it- is that
Yeah,
if
thanks.
it costs you like C to go to that next state,
Right.
your heuristic won't change by more than C. So like in Pac-Man, like if you went one step, your heuristic couldn't change by more than one. Like if your heuristic just jumped by 10 all of a sudden, that would be inconsistent.
Okay, that makes sense.
Yeah, so it has to be the same currency as your path cost. Yeah. You can't use dollars and Bitcoin, because then things would be confusing. Yeah.
This is just a question about totally different thing
Yep.
than heuristics. You sent out on the email that one of the warm-up problems was like, it was like part 2 of warm-up 5, part 2, question 2. You said that you mistakenly put the answer as nothing when it was something else, but
Oh, yeah.
I don't get how it would be, how, the question was like, here's
Yeah.
a graph, what's on time, independent of given alert.
Why don't we pull it up?
I don't get what the sort of answer could be other than nothing.
I think it's actually based on the Markov blanket concept, which is literally just anything in the Markov blanket, it's dependent on, everything else is just not.
But it's dependent on stuff outside of it.
Studies
What do
in
you say?
studies in on times markup blanket.
Yeah, it's,
Yeah, exactly, and but you don't have it.
Right.
You need study to determine learning.
Can you say more things about the question? Or,
Just,
pull it up.
seems to me like nothing is the correct answer.
So it didn't.
It's not the correct answer. They send an email saying nothing.
Yeah, I know. That's why I'm confused. I got the email saying there wasn't the right answer, and I'm not sure why. I'm not sure like what the actually correct answer would be, and I'm not sure why, like, nothing is wrong.
The idea is that in a Bayesian network, something is only dependent on something if you can follow it through following all the arrows one direction or the other direction. So like, if you're following all the arrows downwards from any guy, and anyone who you can reach from another node by following the arrows in a fixed direction is dependent on that guy.
What does that have to
But
do
you
with
can,
Because it's like they're like children. I mean, if you can draw it as an example, like, yeah, it's like if you have car shut down and then you ran out of gas and when your engine broke down, both inform that, and you know that the car shut down. That doesn't tell you anything. Wait.
That
So
the car shuts
so
down,
you're
it
saying
doesn't
that
tell
it's
you
like-
about anything about whether or not the engine failed.
Yeah.
If you're like looking at the oil and see that it's empty.
So what was this warm up number
Part 2.
5, part 2?
5, part 2.
Okay.
Chance slightly.
Yeah, that doesn't seem like it would follow to me. It seems like it would be everything that you can, it seems like, to me, how I was understanding it was that it's that anything that you can reach without going through anything that you're given is dependent.
So I'm fairly certain that's false. It's just you look at the Markov blanket.
Yeah,
So if
yeah.
you are 2 children away, for example, it's not dependent.
But I'm pretty sure it would be, because,
But it's fine not.
but it doesn't make sense.
Normally, you could go as far back up the tree as you wanted to, and technically it might have an effect because you can do a chain of conditional probabilities. But in this case, we're assuming that it's conditional independence between the nodes.
But we're not. We're given that they are dependent using this graph.
So I talked to a grad today and he talked about deseparation. That pretty much explains it.
Okay, so which question was this now?
The question was,
Yeah.
given the node alert, all the nodes that on time is independent of.
Okay, so let's
It says
draw.
Nothing is wrong, but that seems like it would be correct.
and it was originally.
It was originally.
Oh, I erased the did we, you got them? Okay, thanks, Pat. Thank you, Pat. All right. What's that? All right, we can try to do it over here too. Given, but I like to draw because then you can shape things in. So, alert, study. Oh, thank you. Learn AI, have fun. I hope you have fun. And solve problems. I hope you do that too. And on time. Okay, and coffee. So we didn't talk about Markov blankets in class. The reason it's important is, so if we remember, we did talk about the inference in Bayesian network stuff, where we were trying to come up, like basically when you have one of these networks, and then, well, first of all, let's write down the factorization of this.
The alert does have, is
like this?
Yeah.
Okay. So P of study,
So it's P of on time, given.
have fun, learn AI, solve problems, on time, alert, PS. Is this okay? C. What does that equal? How do we write out this factorization?
really enormous table.
Really? Well, yeah, let's start with the factorization, right? So it's P of what? Yeah, press snooze times P of coffee times P of study, yep. And then times P of alert given press snooze and coffee, yep, thank you. Coffee.
P of on time given the same thing.
P of on time given PSA times P of learn AI given study alert on time times P of have fun given learn AI times P of solve problems given learn AI. Okay, and the question is what given what? Given alert, list all the nodes. So we're given alert. So given alert, and we want to know all the nodes that on time is independent of. So this is like there's sort of like two way. What this is really asking is a mathematical statement, right? So if you go back to the definition of independence, A and B are conditionally independent given C of what? Yes, P. Right. Yes. So another way to write that is this, right? If they can factor independently, they're equivalent, right? If it's an if and only if. So I'm just going to write that one because it's a little easier. So it turns out that if we can, so what you want to do is one way to think about this is that for each one of these nodes, we want to check if the distribution of, so for all nodes, so let's say we're given an alert, we want to know if on time. So P of, let's say, on time and coffee given alert equals, we don't know, P of on time given alert, P of coffee given alert, right? And then we can just go, so the question is asking, like, let's just go through all the nodes one at a time and see if we can prove that they're equal or prove that they're not equal, okay? So in some sense, it's really asking something algebraic and not something about the graph. But we didn't, and again, I apologize, we didn't cover this in class and we had on the homework. But I think it's important not to lose sight of the algebraic sort of mathematical connection, because that's really what it's all about. The graph is a tool for helping us figure that out. But at the end of the day, it comes back to the this structure here. So let's take this example of on time and coffee. Do we think which I mean there's kind of a node there, so it's a clue that that maybe maybe that's not true, right? Can we prove that it's not true? Can we convince ourselves that it's not true? So like,
We're just trying to convince ourselves that on time is dependent on coffee, right?
right. So what do we know about this, right? So P of O, OT, and C given A. So we can sort of write it as a joint. Let's see. What's that? Yeah. So, and maybe I'm almost wondering if it's going to be too complicated to do this in a live, but like, what I would do is try to write it as a joint, and basically say, if I marginalize out everything, like, so I have a factor, right, for P of coffee, P of on time, given PS and A. What's that? So I can kind of intuitively see that it's not true because I have this factor here, and like I can't really break it down into something simpler. But to prove it's not true, I think what I'd have to do is some math that I'm scared to start to try to reconstruct, because I'll go down a rabbit hole and do the wrong thing, and then we'll just spend 15 minutes doing algebra. So I can also take this offline and send an email about it. I think that's what I'd rather do. But like basically we can. You have to trust me, I guess, that you can derive a proof that this isn't true, which will come back down to the sum rule and the product rule and the independence assumptions that we've gotten from our graphical model. So if we write it down as a joint and we start marginalizing stuff, we can prove that that's not true. And if we go through these nodes one by one, we can is there a question?
I was just
Yeah.
it does seem fairly intuitive that
Yeah.
on time isn't independent of copy.
Yeah.
Because like you have the, but can you give one where it should be intuitive that it is independent?
Yeah.
That's
Yeah.
what I was sort of asking.
Okay.
No, I mean in that graph.
Oh. Well, let's take a.
Because like in a lot of
Yeah.
it's very clear where it's like, oh, you have one node here and it influences two things, and given that those two are independent.
Yeah.
Those are very clear. That's when they're like already going every which way.
Yeah, if you don't mind, I'm going to do a different graph, and then we can talk about this graph. Like we can sort of talk about the deseparation. So like, see. So let's see if this is D. So are B and D independent of each other? So this is probability of A, B, C, D equals P of D, P of A given D, P of C given A, P of B given A. So basically, if I know A, then so in sort of the full joint, they're not independent, right? Because and sort of intuitively, if I know D, then that tells me something about A, even if I don't know A for sure, and then that's going to tell me something about the children. So like, if I know in this graph, if I know that you had coffee, that tells me something about whether or not you're alert. I don't know for sure whether or not you're alert, but I can condition on that, and I know more things. That distribution is going to change. And then based on that, my learn AI distribution is going to change. That's sort of what this graph is telling us. But now I know alert, okay? And I know let's say I know alert and on time. Let's make it simpler. Or in this case, let's say I just know A. So now are B and C independent of each other? Yeah, why? I know A, yeah. So whatever D could have told me, the only way that I'm assuming D can affect B and C is through A. If I know A for sure, it's completely given to me, then D and C and B are conditionally independent. So what this is saying is probability of C and D given A equals probability of C given A times probability of D given A. And I assert that we can prove this using the sum and product rule, although I'm not going to go through the math of that. Yeah?
Can you, when you have one of these Bayesian networks, can you, when you're given a node,
Yeah.
can you determine if it's independent from another node in the graph just based on whether or not there's a path to get there?
Yeah, so this is, okay, so if I was, and I'm feeling really sad, and if I had prepared a lecture, we would have driven the sum and product rule, but like there's a trick in the graph, and it's not just directly connected. So what there's this notion of the Markov blanket of a node, which is your parents, your children, and your children's parents. So if you're conditioned on these nodes, then if two nodes are sort of separated in the Markov blanket sense, then two nodes become conditionally independent of each other.
That has to be all of them.
It has to be all of them, yeah.
Okay, that explains it.
Right.
When you say
So
independent in general, you're talking about conditionally.
I'm talking about conditionally independent. Yeah, so it's always C and D given A. It's always conditional independence. In the world where these things are observed, yes.
So, like conceptually, instead of like math-wise,
Yeah.
why is study independent from on-time given work if it's still in its Markov blanket?
So study and on time.
Because there's a path right directly to them, right?
Yeah, it would.
So
Learn AI.
your parents and your children. So you don't. You're just given alert, right?
The other two that are independent. But
So we're saying study and what's that?
Did the answer just say that?
Yeah.
It makes it worthwhile to go over what Markov blankets are.
Wait, what's the actual answer?
So what's the Markov blanket?
Study.
So what's the Markov blanket for on time?
Study of
Markov blanket doesn't tell you two things that are conditionally independent. They tell you the set of things you need to be need to condition on to be independent of everything else.
Yes.
The question is which ones are independent of on time.
given
So
what?
if study is independent, that's the answer.
Except I don't see why that would be the
It's in the
answer.
markup blanket.
I think, but
That
that's
makes
the
no
answer.
sense.
Well, we're not getting Markov.
You only have on-time in study, because they both go to learn AI. If you suddenly know for sure that you're on time and that influences learn AI, it doesn't tell you anything about whether you studied or not.
Yeah, it does.
No, it doesn't.
It does.
The reason that you know you learned AI is because of on time. It doesn't tell you anything about studying. If you're for sure certain that it was on time that contributed to learn AI, it doesn't tell you anything about what you know about studying. Well, by that they
would But
always be independent. By that they would always be independent, regardless of
Yeah.
That's true.
Except that's true.
So, but on time and study don't give a 100% chance of learn AI, right? They just give a
Distribution over it, yeah. So if I'm on time, maybe that means I'm more likely to learn AI, and if I'm studying, I'm more likely to learn AI. So that changes the probability of learn AI given that stuff. But study is sort of is like by this construction, we're assuming study just sort of happens. So if we knew learn AI, then that would tell us something about study. Right, like just like like we would know if like just if you knew that you learned AI without knowing anything else, it'd be more likely that you'd studied. If you, but if you know on time, that makes it more likely to learn AI. But like that, but we're assuming that there's these independent factors in the graph, so that means that it is more likely you're going to learn AI, but that's not going to change your prior kind of on studying. Yeah.
So nodes in the Markov blanket of a different node are sometimes independent and sometimes not.
Yes.
Wait, but-
Yeah. Yeah.
Okay, just like, I don't know, what I sort of don't understand is that like, I was under the impression that independent can mean that, but it can also mean that like, A is independent of B if like,
Mm-hmm.
probability of A is the same as probability of A given B.
Yes.
So then, that seems like this would say that study isn't independent because probability of on time is given that you studied will be different because the fact that you studied will change the probability that you learned AI, which will mean that it'll change the probability that you're on time because of Bayes' rule lets you reverse
Mhm.
them.
Yeah, I think what I should probably do is take this offline and write down a better explanation of Markov blankets and stuff, and then send you guys mail. So, because because I'm not like doing a good job of explaining this, and I think, yeah, what's that? Is this going to be on the midterm? I think given the confusion about it, I think it should not be on the midterm, so no, it will not be on the midterm.
All right,
Yeah.
If you weren't given alert, are
Yeah.
you also independent of alerts from on time?
Yeah.
I think not, because press news and.
Doesn't change anything, yeah.
Yeah. So what I want you guys to take away from this, I will send some more information about this over email. But what I want you to take away from this, like what I'm going to go do offline and not try to do in front of you guys, 'cause I don't think it's the best use of our time, is sort of write down the conditional independence definition and then derive it using the sum and product rule. And then we'll talk about the trick of using the Markov blanket. But I wasn't prepared, and honestly, I should probably know how to do it, but I'm not reconstructing it myself right now in front of you, so I apologize for that. But the way that I would try to think about it, like it all comes down to sum and product rule, but there's a trick for quickly figuring out these independence assumptions using the Markov blanket and deseparation. Yes.
Okay, sorry, can I just ask you a quick follow-up question on that?
Yes.
So, since the answer is that study is independent of on-time given alert, is study always going to be independent of on-time regardless of the alert or not? Because like intuitively we were saying, okay, like if you're on time, that'll affect the probability you learn AI, but not that you study. But then, do we need to have that given alert factor? Like, I guess that's my question. Do we need to know that we're given alert?
So if you know learn AI, then these two become dependent on each other, right? So if you know that you learn AI, that tells you something about study and on time, and it tells you about like you can actually derive an expression for them that they're dependent given learn AI. So there's situations in these graphical models where you can be given new information. So not only can giving you information break independence assumptions, it can also make things independent. It can also make things not independent. So I will make sure I put that in what I'll send you guys out. But we won't focus on this in the midterm. The main things for the midterm of what I want you guys to take away is the mapping between this and the factorization and the sum and product rule, the representation of this as a conditional probability table, and how to find different marginal distributions. So summing things out, marginalizing things out, and multiplying things out to get different conditional and marginal distributions for graphs. We don't have a complicated graph like this on the midterm. Okay. I'm just going to make a note of that, if you don't mind. And the reason all this is important is when you guys are doing like inference in a graphical model. If you make a general algorithm for doing inference, like variable elimination, I kind of waved my hands about that in one of the lectures. It uses this stuff extensively to figure out which variables you have to take out to get the marginal distributions in a systematic way. But we didn't talk about that algorithm. Okay. All right, so sort of going back to our review, we talked about local search. So when we don't need the path for the goal, like our little robot is in the building and he's kind of driving around, and it's costly to go somewhere else. So doing something like A star where we can teleport ourselves from one node to another because we have a model of this whole state space in our heads doesn't always work because so the example of that was like a little robot that's driving around in a building. If you search down one hallway, then you can't teleport yourself somewhere else in the building. So there's different algorithms for doing that, and in particular, these greedy methods, and then we implemented a version of depth first search that took into account the cost of moving between different nodes and sort of talked about the trade-off between that. So we're going to definitely have a local search question on the midterm. And then we talked about adversarial search. Yeah?
Was gradient descent after this, or was that part of it?
This was in gradient descent. So we talked, we had a homework question about it, and we also talked about Bronovan's paper in the Microsoft tech support article. So that was sort of part of the applications. I'm not planning on quizzing you about that paper. I think that's more sort of to help you guys see the connections between this stuff and stuff in the real world and get a taste of how these techniques are applied in practice. But I'm not expecting you to like be able to reproduce his equations or implement the algorithm. But it would be good if you had read the paper. Yeah.
So yeah, so then for gradient descent, where does the step size come into the calculation for each iteration?
That's one of the tricks, right? So you can get that from the gradient, or but sometimes people use really small step sizes.
Like
yeah.
if we're given a step size, how do we know how that affects? Like, what does that mean about
Yeah.
what we do for the next iteration?
What does that mean about what you do for the next iteration? Well, you have your thing that you're estimating, and you have your gradient, which says this is what direction I'm going, and the step size. So like let's say this is my function, and my gradient says I'm going this way, right, to get to the top. And in this case, it's like just a derivative that I could take. In real problems, it's multidimensional. It's really complicated. So my gradient says the direction, and my step size says how far am I going to go in this direction. So if I go really far and then I check, like I think I'm going to get a reward up here, but actually I'll be down here. Or if I go even farther, maybe I'll go really far, and then I check, I might actually get a low reward. So the sort of general rule about it is small step sizes are safer because you're less likely to do this, like overshoot and not hit your local maximum. But large step sizes are better because they can move you farther through the state space. So we talked about simulated annealing to kind of address that problem, where at the beginning you take larger step sizes to explore the space, and then you decrease the step size so that at the end you end up near a local maximum.
Yeah, I don't know if we're like allowed to be talking about specific problems from the practice midterm.
Yeah,
but I
please.
was confused.
Yeah, you're allowed to collaborate on the practice midterm, just not on the real midterm.
Yeah, I was confused about I was confused about the local search one where it says given we are at x equals 10 and step size is 0.1, how that gets us to 8 on consideration.
Sorry, which question?
It's question 3.
Let me pull it up.
I think I can clarify that. If
Okay.
You take a step that's equal to the step size times the gradient evaluated at that point. So the gradient evaluated at that point would be negative 20, and then you multiply that by 0.1. So taking a step equal to 2. So then you would move from 10 to 8.
So you multiply the step size by the
Yeah, that's like
gradient.
the general gradient descent formula. There are like tons of variables like we talked about like
Okay, great.
So it's a coincidence that when you draw a line with the intersection, it intersects the. If you draw a line of gradient 2x intersecting 100, the only other point it intersects, y equals x squared, is at 864.
that would be a coincidence because, yeah, that's a pretty
Can you repeat what you said?
Yeah, sure. In like the general gradient descent algorithm, you take a step that's equal to the step size multiplied by the gradient evaluated at a point. So since we're descending, the gradient, we pick the negative direction. So that would be, since the gradient is 2x, that would be negative 20. And then you multiply that by the step size, which is 0.01. 0.1, sorry. So then you get a negative 2, so then you move from x equals 10 times equal to.
Does that help?
Yeah, that's
okay.
Exactly.
All right. Yeah.
I had a general question about the exam.
Yeah.
Are we getting 2 tries for each question, like on the homework, or is it going to be?
Yeah, so my plan right now, based on what we talked about in class last time, is to have you guys have 2 tries, and then you will find out whether you got it right or wrong for the auto-graded ones right away. You won't be able to change it afterwards. If you have a problem with that or a question about the midterm, I'm going to ask you to save it for after. So like, you can write it down, and I hope there's no mistakes, but maybe there will be. And talk to us after the midterm about any issues that you come up with. Just go focus on completing the rest of the exam. And we'll try to be fair about educating those kinds of issues. I'm hoping that finding out whether you got it right, like it seemed like in an informal poll in the class last time that you'd rather know that rather than not knowing. I'm seeing most of your heads nodding. We are going to do it a little bit differently though, because it's going to be chunks. So there'll be like, in one of these chunks, you'll get like 3 or 4 questions that are related, and you'll have to check them all at once. So you won't be able to answer one and then check, and then answer another and then check. You'll get to check them in related chunks, and it'll say something, these ones are right and these other ones are wrong, and then you can fix it and then check it again, and then that'll be the end. Does that sound okay? Okay.
I just have a question
Yeah.
about particle filter.
Yeah.
So the probability of sampling any specific point,
Mm-hmm.
it seems like in the project we kind of like draw them uniformly. So like each one, I'm not sure though. Like either would you each one like it's.
So when you initialize it, usually you sample from like a uniform distribution. And then as you update and stuff, you keep the ones that look good and you downrank the ones that don't look good using the Gaussian estimates.
But is there a way like to calculate them as in the practice midterm?
So I don't know. Where's the question about it?
I feel like I've never seen this kind of questioning.
Yeah.
Just if we didn't need information about where it is, like.
Yeah, so we're telling you the weight. So you have to.
Oh, got it, okay.
So you have to. So basically, the weight is what's going to tell you how to sample the particles. You're doing weighted sampling in a particle filter. So uniform sampling would be all the weights are 1. I'm just going to pick a particle. Weighted sampling means I'm more likely to sample ones with higher weight. So I sum up the weights and divide, and then that tells me which one to pull out. Does that help?
Yep.
Okay. All right. What else? Yeah.
Another general question about
Yeah.
Midterm?
Yeah.
So are we allowed to open up a Python shell or something to do like use the calculator?
No, we will not let you. Oh, there's going to be a little bit of calculation. We're keeping the calculation simple.
Can we bring a calculator?
No. Yes. You have to use your hands. No, you may have you can use you can use a slide rule. Yeah, there's going to be some calculation. I'm keeping the calculation simple, and the reason for that is that it's going to be a proctored midterm, and I don't in principle have a problem with you using Python, but I think it's going to be too hard for the TAs to keep track of exactly what you're doing in the Python terminal. And so I think that it's simpler just to say, like what I'm going to suggest that you do is like make this window at the beginning of the test, make it always on top and maximize it, and then don't open any other windows during the test. And we'll have instructions for this, but like I think that keeps it really simple, like what we expect you to do, and any other windows open or anything like that is a violation of the policy. Okay? All right. All right, so local search, adversarial search, so alpha beta pruning, the difference between a policy versus a plan and what that meant. So not only did you just know what your sequence of moves would be, but you had to know how you were going to respond no matter what the other guy does in an uncertain environment. And the idea that alpha beta pruning was an improving on minimax, so we were able to not have to search all the branches in the tree. If our adversary would we just knew that our adversary would never go down that route, and the magic of the scoring function. So, and if you remember, it was actually that really interesting tic-tac-toe scenario that was happening in alpha beta pruning because a human would have taken the shortest path. Like we had this situation where the computer was making a really funny move, where it could have won and it didn't. In lecture, and the reason it was doing that is because the other, like it could have won right away, or it could have taken another move, which also would have needed it to win just a little bit longer. And there was no trade-off. There was no reason for it not to do that because in any case it was going to win. So sometimes these algorithms don't do what we expect, but they was still optimizing this function of trying to win. I like that bug. It was fun. So. I don't know if you guys, I have like this list of like the awesomest bugs I've ever run across, and that was a pretty good one. All right, the probability stuff. So we talked about Jaynes, the sum rule, and the product rule. The mapping between a problem description and equations and numbers. So we're gonna give you a problem with a graphical model, but we're not gonna give you like the CPTs. We're gonna try to sort of explain a sort of real life situation in words, and then ask you to write down the CPTs on paper and then use them to compute a conditional distribution. So conditional probability table. Yeah. So the computations hopefully won't be too complicated, but and then the idea of a multinomial distribution, which boils down to the CPT. So the conditional probability table, where the different values of the variables each have a discrete probability, and they all have to sum to 1. And this is one parametric representation for a distribution. You guys, and we talked about this a lot in lecture. In almost all of our lecture, we talked about it very little, and for the project, of course, you're using a different parametric representation, using the Gaussian with a mean and a covariance. So this idea that we have one choice, which is the CPT, which a lot of people use a lot of times, but there's many other choices too, and lots of trade-offs that happen as you make these choices. So graphical models. The mapping between the model and the factorization, so being able to write down the factorization that corresponds to the model, and then using that representation to get different conditional and marginal distributions that you need out. So we're going to ask you to do that on the midterm. And then Bayes filtering and particle filtering, so you should be familiar with the graphical structure of the filter as one particular graphical model. We had some slides about it. I had a simple implementation in class with CPTs, if you remember the localization thing, where we were trying to localize in a room with a 3-room house with a bed detector, I think it was, and and we saw that as we moved around you could localize, but also as you observed things you could localize, and over time it got a better and better estimate in sort of the high-level structure. And the representation of the distribution is weighted sample. So that was the midterm practice question that we just went over. What does that mean about how you compute the sample from the distribution by averaging and stuff? Okay, so that's sort of the content. We've sort of interleaved it with questions. And we have a few more minutes, so I'm happy to take more questions, or we can start going through more practice problems. Yeah?
After you get the factorization, I'm a little confused that you derive other probabilities from that.
Yep. So it always boils down to the sum rule and the product rule. So for example, if you wanna write in this graphical model, you're given A and you want C. So let's say probability of C given A. I would write that as the joint A, B, C, D. And then I would sum out over C and A. So, first I guess I would first make it given A, so I would divide by A. And then I would sum out the other variables B and C, and I would sum out B, C, D. B, C, D. Is it,
since we want C, we're summing over C?
You are correct. This should be D. So this would give, okay, I'm skipping steps, but so I would write this as probability of A, C over probability of A, product rule.
Can't see, sir.
Probability of A and C divided by probability of A, and then I would use the sum rule to write these in terms of the joint. So this is B, D, probability of A, B, C, D, B, D. And then the denominator is summation over B, C, D, probability of A, B, C, D. And then this is the factored representation. The joint is the factored. So you should be familiar with doing that kind of thing.
What did you say at the end? This is the what?
The joint distribution then is factored using the graphical model, and then you can always just plug in all the numbers. Sometimes when you do this, more things cancel, and you don't have to do all the numbers. But we won't. So you should be comfortable with doing those kinds of manipulations. And if at the end of the day you always go back to the sum and the product rule, you'll find the path. The best way to get comfortable, if you're not, is to just start drawing some models and then pick two of the variables and start writing P of A given B, P of B given A, P of C given D for different models, and then write it out, check it with a friend, check it with a TA. Yeah?
At what point, like, do you have, like, the answer? Do you, like, for, like, the tests and stuff, would you want us to factor it? Like, if we give you the factorization and then
Yeah.
the sums, is
So there's a few questions where it's multiple choice, where we're asking, we're basically, we say, we give you a model and we say, write PSC given A, and then we give you like 5 choices. And you have to pick the right one. So I didn't want you to have to like type in formulas, but I wanted you to be able to do that kind of manipulation.
Okay, so you would have
And
to
then
take that, do all the sums, and then do all the algebra to get down to
a simplified form, yeah. Uh-huh.
Okay.
Yeah, it's not going to be that complicated, but
Yeah.
that kind of manipulation. And then plugging in numbers to actually get actual numbers.
Is the parametric form like putting in separate conditional tables?
Conditional probability tables are one way of doing a parametric form for these distributions. It's it's the one we've used the most in lecture. So I want you to be comfortable with them. And you should be comfortable with filling them out and manipulating them and using them, like doing this kind of algebraic manipulation and then going to the TPT conditional probability table and plugging in the right numbers to get an answer. I also want you guys to know that it's just one and there's others that we could pick, and you saw that concretely in a particle filter. So I don't want you to get too hung up on it has to be a CPT all the time, because it doesn't. Yes?
Could you start to write out that sum so we can see what it looks like?
Which sum?
Either of those.
Okay, yeah, so all it is taking this and replacing it with the joint.
Why do you need B in that, though? Because A doesn't depend on B.
A doesn't depend on B. Yeah, so we would probably find, why do we need B then? Because A doesn't depend on B. We would probably,
Sum over the different possibilities, but
yeah.
like if you're finding, for example, like let's just talk about the probability of A.
Yeah.
Wouldn't you only need to sum over like given
Yeah, so-
D and not D, not there? Like I don't see why B would factor in at all. But in the graph that you draw.
Yeah, so if B doesn't factor in, it'll cancel. And if it does factor in, it won't cancel. So what I was doing right now is like staring and trying to see if it canceled out.
Gotcha.
Does that make sense?
Yeah.
So the answer to that question will identically sort of depend on whether or not it cancels.
Okay, so you
And it's very unintuitive. There's just some really funky, maybe one of the things I'll send out is like there's some really funky graphs where really unintuitive things happen where you're like, damn it should cancel, and it doesn't. And so I've gotten this habit of like really being religious about like just trusting the math rather than my intuitions about it, which means I'm not good at doing deseparation and Markov blankets, which is why I failed to answer that question effectively in class just now. So does that help though? Like if it really didn't need it, it would cancel out. So if we wrote out these two factors and then we'd find something would pull out of the summation or something and it would be okay. Okay? There'd be factors that didn't depend on anything that we're summing over and we could just take them out. Yes?
On the practice midterm, what is the distinction between number of ingredients in the mixing bowl and number of containers poured?
Question number?
I think it's number 2, like the second page. Yeah. It's down towards the top.
So,
So the state space description is up here.
So
Yeah, we're running out of time.
I asked the TA about that.
Yeah?
Basically, you have multiple bowls at once, and there's one that's your actual mixing bowl. So there's ingredients inside your mixing bowl, and there could be other ingredients poured in other bowls too. So you have like more than one bowl.
So if you have like ingredients that you haven't used yet and stuff. So I can text you a question after class. Thank you guys for coming. There's TA hours. We're actually moving more of our hours earlier in the week. So if you have questions, you can come. And we'll see you on Thursday. Yeah.
Yeah, so